It's trivial. It's a whole time.
All right, there's a quiz. I guess it didn't save the 1 point question, so it's an easy one. So, all right. So, we talking about graphs last time, and so just to remind people, this is around where we stopped, right? So a graph is basically a bunch of edges that connect nodes. Oops. This one? Yeah. So something like this. So I now want to talk about how to represent those. So I'll skip the terminology a little bit, and I'll talk about implementing graphs. Oh, hello. There's a quiz, but it's an easy one. So here are two options. So here are two options in terms of how you can implement a graph. So you can imagine thinking about it as what's called an adjacency matrix. So this would be kind of a square matrix, and you would just put in 1 if there is an edge between the ith vertex and the jth vertex, and otherwise it would be 0. So that would look kind of something like this, right? So here, for example, there is an edge between. Hello, there is a quiz. Was there a test today or something?
There's an MSc quiz.
Oh, okay. Well, there is an ESC190 quiz. It's probably much more fun. So sorry. So to repeat for the people who were just coming in, we're talking about how to represent a graph in memory, right? So you can say, okay, so I want a square matrix. So if I have 9 nodes here, so the nodes are like, 0 and 1 and 2 and so on, then if there is an edge between, for example, 0 and 5, then there would be a 1 over here because there is an edge from 0 to 5. So that's the 1. Anywhere where there is not an edge, you would put in a 0. Yes.
But like, where do I find these nodes? Because I can't see them on the website.
So if you go to the slides, you go to the last slide, there is a link to the, yeah. Okay. Make sense? So, okay. So let's now try to implement that. So that's the adjacency matrix. So what would I be doing here? So this is not in the notes. We will put the code in the notes after the lecture. But I think, again, it's kind of good to follow along. So this would be graph. So here's kind of the design. I'll have a class graph. I'll turn off Copilot because that's just boring. So I have my class graph, and I'll start with my init. And I'll complete it later. So what do I want to be able to do with the graph? Well, at the very least, I want to be able to say kind of are connected for node I and node J. So let's call it is edge. And I want to say put edge. And I want to say remove edge. So if you remember, this is kind of the concept of having an abstract data type, right? So I can imagine multiple ways of storing this in memory. And right now we'll do the adjacency matrix. But you could imagine just taking the skeleton and implementing it in various ways. Yes. So I and J would be two nodes. So I and J. So if you look here, so the nodes are numbered in some way. Self is the graph, right? So if you remember, the way we implement those things in Python is we send in the object every time. And then we look up inside the object, for example, like in this object, is there an edge between I and J? Right. So in order to know whether there's an edge between I and J, you need to send in the actual object. Yeah. Say again? Would we? Sorry, can you speak up? About a week and a half ago. Okay. Yes.
So basically, are these like, just to refer to like abstract data types, are these like the general operations of the graph?
Exactly. Yeah. So like there could be more, but this is what I'm doing for now. Yeah.
Edge the circle or is edge the line?
Edge is the line, right? So let's go back to let's quickly go back to the terminology. So we have vertices, or sometimes we call them nodes, and we have edges. So edges are the lines that connect or the connections between the nodes.
Okay, and if there's a connection between the two nodes, then we put like a one in the adjacency.
Right.
Oh.
Yes.
So because it's like you can have MIJ and then MJI, like if it's direction based,
that's right. So one way, we'll get to that. I just first want to do the implementation. So one way to think about it is those are directed. So if you can see, so here you see kind of the arrow. So there is an edge from 7 to 8, but not from 8 to 7. You could imagine if you want undirected, and often that is what you would do, is that if there is a connection both ways, you would just put in a 1 for row 7, column 8, and also row 8, column 7. So right now, row 8, column 7 is 0, but you can imagine making it 1. And then there would be a connection both ways. Make sense? So, okay. So this is kind of the skeleton. So now what I want to do is I want to implement it somehow. And the idea is we'll do it with an adjacency matrix. So we need to set up a matrix, right? So this is probably not syntax that you would necessarily remember from lab 8 of ESC190. But this is one way to set up a matrix. So I'll just quickly remind you. So you can set up a 10 by 10 matrix like this, for example. Right? And then you can access it like so, for example. Right? So row 0, column 1. Make sense? So what's the idea here? We'll store a matrix inside of the graph object. And then we'll access the matrix when querying edges. Right? So that means that we need to tell init the size of the graph initially. So if we want to be able to resize it, we'll have to figure out something more. We'll do that after. So this would be the number of nodes. And now here you can say, okay, so self dot this is going to be this array. Make sense? Yeah.
So like, what's the benefit of using like a numpy array versus just like making like a list of lists?
Making a list of lists is kind of annoying. So in order to make a list of lists, with the syntax that we have, you would need to basically create each row and then do a for loop, creating each row separately. Like, it's not hard, but this is like nicer.
Okay.
Okay, it's also slightly more efficient. So, okay. So how would we do is edge? Well, we'll just check whether. So I'll do zeros so that they don't need. So it would initialize it anyway, but this would explicitly initialize it with zeros. Okay, so if I want to do this, I'll just check whether the corresponding thing is 1 or 0. So this would be adjacency matrix at I at j. Is it equal to 1 or 0? If it's equal to 1, I'll return true. If it's equal to 0, I'll return false. Yes.
So when you initialize it without saying zeros, is it just a bunch of numbers?
No, it's going to be 0. Yeah. Okay. So in order to put the edge, I'll do the same thing. So I'll just copy this. and I'll make it to 1. If I want to remove it, I'll make it to 0. So let me review how we use it and what the syntax means. So if I say G is graph, let's say 4, like this, then if I say something like so if I say something like G dot put edge 1, 2, that's the same as saying graph dot put edge G 1, 2, in the same way that this is the same as graph dot init four. So here what we're doing is so kind of G, which is not yet defined, but 4, right? So here what we're doing essentially is we're automating this process of always passing G to the functions. So we're creating the adjacency matrix inside of G so that we can then just say G put edge and we access the adjacency matrix that's specific to this G. Does this make sense to everyone, or do people want more review? Yeah.
Discuss something about the syntax.
Okay.
So like graph init G4, like would we have to declare G beforehand?
Exactly. So like this is why I said that this is kind of pretend. So like init is special in that like it's not so you can't quite call it like this, right? Like this.
But we need to declare G before.
No, so like init is special. So this is, like I said, this is like pretend, right? You can't do this, but you can do this. So this is passing 4 to here, and then that creates the G. Yeah.
Wanted to do it like graph underscore init whatever. Then
No, yeah, that's not the thing.
oh, then I do G is done before and then
Say it.
I do G is done and then on the next line.
No, I actually I don't believe there is a way to do it.
Okay.
Yeah, it might be wrong. Yeah.
G takes the graph or it automatically goes to graph and runs the init line.
Exactly. So it calls the init, and so init is special, so it creates the G. So in the same way that in C we have like the manual create node or whatever, right? So this is kind of the equivalent of that, but it's automated. Yeah. So G is the so okay. I say that there's a lot of questions. Who wants a review of this from? We had done this, but who wants a review of this from the start? Okay, I think we're doing that. Okay, all right. So let's again do what? So let's. So let's do the class student, right? So this is how it works. So I'll just quickly do like this. So I'll explain this in a second. What do you want? So I'll do like get GPA or something. Well, get GPA is boring. I'll do print student. So I'll do like name. Oh, there's no name. It's just major. So this is the major and this is the GPA, and we'll print a separate one and we'll say I don't actually know what you got the dean's list for, but let's say it's 3.6. Okay. So this is how you create a student. So Robo is currently the biggest major. I don't know what the average GPA there is, but let's say optimistically 3.8, probably not. So something like this. So what does this do? This is kind of like calling the init function. Inside the init function, what you're doing is you're creating this S, and then you are storing whatever you want in the S. Right? So if you were to think about it in C, it would be kind of like so obviously this is kind of made up, but like something like this. So like whatever, and then you would say so this is kind of equivalent to this, except more convenient. Does that make sense? Questions? Okay, is that good? So, okay. This has an error, so this would be like this, right? Anyway, this is like fake C anyhow. All right. So you are you can create multiple, right? So you can create like an S2 that's, you know, MI with 3.9, whatever, and then you can access those the way you can access elements of the string. So you can access s.major, for example, and that would be robo. And you can access like s2.gpa, and that would be 3.9. Does that make sense so far? Yes? No? Okay. So you can also call the functions in here. So I can say, for example, s.printStudent. And that's the same as saying s.printStudent of s, right? So it's just a more convenient way of doing it. So the self here is this guy. Make sense? And then this would just print it. So let's try to run this. So I'll say, I actually already have this, so I'll just run. Syntax error. Oh, okay, C is not actually valid Python. Comment this out. And there you have it, right? So here we called the print student and it printed this. Make sense? So let's not, just because we're doing this anyway, let's do a data structure. But first I want to ask, like, does this make sense? Does this not make sense? Okay, So let's do a data structure. So we did queues this way, and you did that in the lab. I want to do a similar data structure to queues, which we would need anyway later, which is the stack. So the idea with stacks is, so this is called LIFO, last in, first out. So it's a collection of elements, and the operations are push and pop. And push is put an element into the stack. And pop is get the last element that was put onto the stack and remove that element. So it would work kind of like this. So if I say like push 5, and then I say push 10, and then I say push 2, and then say pop, this would return 2. And if I say pop again, it would return 10. And if I say push 20, and then I say pop, this would return 20. Does that make sense? So it's basically like a queue, except the unfair kind, right? So the last that got in is the first that gets out. So that's kind of the LIFO acronym. Is that making sense to people? All right, let's see what Discord is saying. Nothing interesting. Okay. So is that making sense? Is that not making sense? I feel like the quiz in the previous lecture is kind of hasn't done anyone any favors. So how can we implement this? So we can keep a list, right? So if you push 5, you'll put it in the list. You push 10, you put it in the list. You push 2, you put it in the list. And then pop is just removing the last element from the list, right? So you just get the 2 and you remove it. And then you get the 10 and you remove it. And then push, again, puts 20 at the end of the list. And then pop, again, just removes it. Okay, so that's the process. So we can just keep a list that basically append to the end of the list, get elements from the end of the list as well. So, okay, let's define that. So that would be like this. So initially, it would be just the empty list. And then when we push, we append. When we pop, we get the element from the end of the list. So here there is, it's kind of a thing in Python where if you remember, I think we mentioned it briefly, list.pop actually exists. So if you do like a list that's like this, and you say l.pop, that returns 2, and the list becomes 5, 6, 10, which is actually exactly what we want. Okay, so I can do that like this. How many people knew that? Probably not very many. Oh, some people. So I can just say self data pop, and I just return that. Or I guess kind of in the syntax that you know, just so that it's maybe slightly less confusing, I can say, the return value is going to be the last element. And then I'll just remove the last element, right? So really, I would do this like this, but that would probably be confusing. So yeah, makes sense. So now let me use this. So I'll create my stack. So here there's no parameters other than self. So this would be just like this. And then I'll try to use it. So this would be like push 5 and push 10. And I want to pop. So I'll print this. So this is supposed to be 10 because 10 is the last thing that got pushed. I'll push 15. And if I pop again, that's supposed to be 15. Is that making sense? Is that not making sense? Not making sense to anyone? Yeah. No, it should be it should be 15 because the last thing that got pushed that's still in is the thing that we get back. Okay, so let me run this. Yeah.
The name that was made inside the class or out?
Oh yeah, thank you. That is a problem. Okay, it's not happy about this. Oh, the remove is by value, sorry. Okay, so okay, I'll just do the pop. Okay. Okay, does that make sense to everyone now? So basically the idea is we store basically just a list inside of the class so that we can implement those push and pop operations. So in the same way, going back to the graph, what I want to do is I want to store my specific implementation inside the object. And then the functions are just used to interact with the graph. Make sense? And the way it would work, so this again should be actually outside. So Shift Tab, by the way, to move thing outside. So the way it would work is I'm calling the graph. So here I'm saying what the number of nodes is going to be. And I'm basically saying initially the graph is going to be empty. And then I'm putting in the edge. So this is not supposed to have any output. But if I now ask whether there is an edge there, so this is edge. Then this is now supposed to return true. And it does. Okay, is that all making sense now? Questions? Is that still not making sense to anyone? All right. So this is kind of one implementation that you can imagine with just the minimal operations that are, is there an edge, is there not an edge? So if you wanted to have a weighted graph, so if you remember where we have, costs of moving between airports and stuff, you can imagine an adjacency matrix like this, where instead of ones and zeros, you put in the weights of the edges over here. In this case, this is symmetric because it's undirected. So ordinarily what you would do is you would just store anything twice. There is a choice as far as what to do about edges that don't exist. Often you might put infinity because if you think about it as the cost of going from here to here, then the cost of traversing an edge that doesn't exist is infinity. So if you're thinking about finding like the cheapest way of getting from this node to this node or something, then it makes sense to put in infinity as the special situation where there's not an edge. Here's another way of storing the same graph. So this is called the adjacency list representation. And what you might imagine doing is saying, okay, so I'll have a bunch of linked lists. So for each node, for example, for node 7 that's connected to both 2 and 8, what I'm going to do is I'm going to have a linked list that contains all the neighbors of the node. So here you have node 7, and its neighbors are 2 and 8. And we store them as a linked list. You also have a list of all the nodes. Make sense? So here again, if it's undirected, then you would just say that 0 is connected to 1. So this would be like this, and you could store the weight of the edge as well. And 1 is also connected to 0, and here the weight of the connection of 1 to 0 is the same because it's undirected. Make sense? So why talk about the different ways of doing this? Well, because the complexity of the operations is different depending on how you actually store the graph, right? So you can ask, is there an edge between the ith and the j vertex? And if it's the adjacency matrix representation, so if it's like is edge, then this is all 1, right? Because you just go into the matrix and you check whether the edge is 1 or 0. On the other hand, if you're using an adjacency list, then this would be of D. So the degree, we'll go over the terminology later, I feel, because we kind of got into the code. So the degree would be just the maximum number of edges that go out of the node, right? And that makes sense, right? So if you want to know whether 3 is neighbors with anything else, you have to go through the entire linked list that comes out of node 3. If you want to do it for 0, you need to go through this linked list. So the complexity would be the largest linked list that exists in this graph. Yes.
So, I guess like summarize in a sense, like the adjacency list method, is that just a linked list where each node has a linked
It's
list?
a bunch of linked lists. Yeah. Is that making sense? So, okay. So let's say that you want to find all the vertices that are adjacent to a particular vertex, right? So if it's an adjacency matrix, well, you need to go through the list of the vertices in order to find the vertex that you're interested in, and you also then need to go and find, go and find all the neighbors. So that would be O of D. So again, the maximum length of the linked list. For the adjacency matrix, you have to go through the entire row of the matrix. Right? So the complexity would be O of the size of the set of vertices. Because here, what are all the neighbors of 5? Well, you have to go through this entire thing. So if you have a graph where you have quite few connections, but a lot of nodes, then it would be more expensive, conceivably, if you use the adjacency matrix representation. Because in the adjacency matrix representation, you have to go through the entire row. In the adjacency list, if you know that you only have just a few connections, then possibly the adjacency list would be more efficient, because you only need to go through the one linked list, which might be short. So, okay. But this is kind of slightly theoretical. Or is there an edge? Or for an edge, obviously, the adjacency matrix is more efficient. The space requirements, though, can be quite different, right? So if you have an extremely large matrix and you store it as just not a sparse matrix, but just as a matrix, then the requirements for space are O of V squared, size of V squared, right? And that's because you need to store the entire square matrix. So an example of a graph where this would be completely infeasible is, all the web pages where an edge is whether one web page links to another web page. That's what Google uses in order to rank your search results, right? So pages that get linked a lot go up in the ranking of the results. Pages that are not linked a lot go down. You can't possibly represent, or you could, but it would take a lot to store a matrix that's the square of the number of web pages on the internet, right? That's a lot of possible links. For adjacency list, if you have basically what do you need? So you need to store all the neighbors of each of the vertices. So how many neighbors do you store in total? Well, as many as there are connections in the graph, right? So storing all of those, that is O of E. So if it's undirected, it's like 2 times E. But the total number of all the nodes here and all the linked lists is just proportional to the number of edges. You also need to store at least something for each vertex. So that is where the complexity of O of size of V plus size of E comes from. Right? Yeah.
For the adjacency list, you scroll up.
Uh-huh.
Why is the 3 connected to the 1?
Why is the
Next layout.
why is the 3? Wait, is it?
Next word.
Oh, the next one? This one?
Like when you're connecting it, you're going from the very first one 0 to 2,
Okay.
then 2 to 5.
So it's not 0 to 2, 2 to 5. It's that 0 has the neighbors 2 and 5. So you're storing a list of the neighbors for each node. Right? So 0 connects to 2 and 0 connects to 5. So this is why 0 has a list of neighbors. That's 2 and 5. And then, for example, what else has like 2 connections? I guess 5 has 2 connections. So 5 is connected to 3 and 5 is connected to 7. So this is why 5 has the neighbors 3 and 7.
Is it equivalent to saying like 5 but like 7 and then 7?
No, so the way it is for each node you store a list of all the neighbors, right? So I'm saying 0 has the neighbors 2 and 5, so 0 is connected to 5 and 0 is connected to 2. Okay, so don't think about it. So like the graph is what's on the left. This is how it's stored, right? So those are different. And if you're storing a list, like it has to be like one way to do it is linked list. And there's other options as well, but that creates its own difficulties. Yeah.
Is this supposed to be a linked list or just like a list that you?
I mean, it is a list. You can imagine storing it using something other than linked list. But in this particular implementation, you're using a linked list. So if we're thinking about, so why think about the linked list? Because you got to eventually also think about putting in the edge, right? So if you want to connect 3 to 7 or something, then you need to think about the complexity of inserting this connection into this structure. So if it's a linked list, then that's reasonably easy. You can just do it in O of 1. If it's an array, like an array list, then it's potentially O of D, because you might potentially need to expand the array list. Make sense? Okay, who is not with me on this? Because I feel like nobody is. Yeah. All right. Okay. So, all right. So that's the space requirements. So yeah. So kind of the point of this is there are trade-offs. Yes.
B plus again.
Yeah. So we are asking how much space do you need in order to store the adjacency list? So here's an adjacency list. So we need to store everything that's on the right. So in order to store everything that's on the right, what do we need? Well, we need to store this column. This column, how much is it? Well, as many as there are nodes. And then we need to store all of those guys collectively, right? So how many of those guys are there collectively? Well, as many as there are neighbors in sum. So like how many neighbors does 0 have? How many neighbors does 1 have? How many neighbors does 2 have? And so on. What's the total number of neighbors? Well, it's the same as the number of edges, because each edge corresponds to a pair of neighbors. Make sense? All right. That seemed hard. Okay, I think we're gonna go now, and I'll see you tomorrow. Bye. Do you want to announce the thing or the integration, or I don't know? Anyway, yeah, no, okay. Anyway, all right, okay. I will see you on Thursday, which is tomorrow. Bye.
This was like a limited list.